say how grateful we are for your generosity. Turn it over to Dr. Carl Meyer to say a few words, and then turn it over to Dr. Eargle.
It's always so gratifying to see an old student come back who has been successful, and Dr. Eargle certainly is an example of that, but it's even more gratifying when they actually bring something back to return. Let me introduce you to Marvin. I hate to say this, but he told me he was a graduate of Carolina.
Look at the shirt. I've got red and I've got light blue. That's me. I'm a mixture.
He was a Moorhead Scholar at Carolina. Then he came to NC State in 1963, got a master's degree, and then finished a PhD degree in 1968 under direction of Dr. Walter Harrington. Many of you don't remember Dr. Harrington. He was at one time department head here for a short period of time. After graduation, Marvin went into academia. He became hard times. Marvin and I were talking about the hard times in the 70s to get a job in academics, and it was really hard. Marvin got a nice position at Appalachian State, but he understood that the industrial world had more to offer than academics, and he went to work for a company called E-Systems in Greenville, Texas, where they developed airborne reconnaissance systems for airplanes in the United States Air Force and NATO airplanes. And Marvin was instrumental in developing antenna arrays for signal reception and direction finding. He then had an opportunity to go to a young startup company named Concept in Rockwell, Texas, where he finished his career, correct?
Yeah.
Correct. And the company was eventually bought out by a system called E3 Communications, where their primary product was something called Network in the Sky, which turned out to be a pivotal product in defense for the United States and probably NATO nations in general. He stayed at Concept until 2004, took the money and ran. And he and his wife, Patricia, moved back to North Carolina and are enjoying the good life. There was going to be a reception immediately after this. In addition, Marvin's going to talk to undergraduates about Pythagorean triples later on, and that lecture is going to be in 2102 for students who would like to learn about that. So Marvin's going to tell us a little bit about airborne reconnaissance today. Let's welcome Marvin.
Well, thank you very much. I'm hoping my voice holds through this. I'm not used to talking before bunches anymore. Airborne reconnaissance. Let me tell you a little bit about the format of the presentation. We worked with a company that delivered products to military people. We were in the defense industry. We had contractual obligations to do reports on the stuff that we were doing on a fairly regular basis. And those reports needed to take the form of PowerPoints, and they needed to be self-contained. That means that there is a whole lot of stuff on the screen that I'll probably end up reading to you. Now that ain't good pedagogy. You're not supposed to do that. But you know, I got into the habit of doing that in the business. So there will be it's not completely self-contained, but there will be a lot of stuff I will basically read to you off the screen, just in case you can't read whatever it is I'm doing. And here's what we're going to do. Talk about terminology, look at some pretty airplanes, wave a little bit at some targets, then talk about the target location, sometimes called emitter location. What we're doing is flying around in the neighborhood of a wartime situation. listening to everything that's out there. We are strictly a passive kind of operation. We suck up whatever information is there, process it, deliver it to the folks that paid the money and who want to take action. That they make the decisions about taking the action, we simply provide information. Airborne Reconnaissance. Here's what reconnaissance is. It's a search for useful military information. Info such as command and control centers. Those are the communication centers that are commanding the battlefield. And surface-to-air missile sites. Those are typically radar sites. So we want to locate, identify the radars, locate them, tell what they're up to. Generally, electronic warfare exploits the radio frequency spectrum. We receive the signals, we identify them. They come in two categories, communication signals and radar signals. Locate the source. What we do basically is fly the airplane along, receive the signal, establish the direction that the signal came from, create a line of bearing by using the aircraft's navigation system to locate, and line of bearing, collect multiple lines of bearing, locate target, put down error ellipse. That's the story. The information extraction comes from the communication signals. The operators aboard the airplane are linguists. They are experts in the language of the country or the country that we're working in. So they can gist the conversations, summarize the conversation, record everything they see and hear, and evaluate the threat and report the results. When I started, this whole process took hours and hours and hours. The aircraft would fly along the border, look inland, seeing what it could receive, record everything it could find. Remember, you probably too young to remember. IBM had this great big tape reels. They were about yay big, probably 6 feet tall, 2 humongous tapes. And we would collect everything on those tapes, bring it home, take it to a 3-letter organization, and let them process it overnight. They would do mission planning for the next day's strikes, then we would go on with them. By the time I finished, all of this was being done in real time. We had a network of aircraft in the sky over the field of interest, each one collecting data on the same target, locating that target within a matter of sometimes seconds, maybe minutes, reporting it to the folks that had to do something about it, and they could take action immediately. So we went from a 24-hour cycle to basically a minutes cycle. So that things changed over the years. Probably getting ahead of myself. 2 flavors of intelligence. Signals intelligence is signal intelligence. It comes in 2 flavors. Do I have a point of view of that? Comment is communications intelligence. In the frequency world, that's typically from the 15s megahertz up to 500 megahertz. Electronic intelligence is stuff above 500 megahertz. The communication stuff is voice, primarily. It's radio, it's TV signals, it's military communications, it's that sort of stuff. The ELINT typically is radar. It's higher frequency radar type signals. The goal is to identify the radar, tell what it's up to. They come in many flavors, and we may talk about that in a moment. Locate. We deal with locate. HUMINT is called human intelligence, and we didn't do that. Comment. Signal externals, frequency range, typically 10 to 500 megahertz. AMs, FMs, and so on. We did Morse code. Direction. A big deal is to ascertain the direction of arrival of the signal to the platform aircraft. Signal internals, stuff we get from listening to the signal. Whatever the conversation's about, we want to know and take action upon it. ELINT, almost always radars. Above 500 megahertz. Radar pulse patterns have all sorts of information in them. pulse width, pulse repetition frequency, intra-pulse modulation, inter-pulse modulation, all kinds of pulses. And there are different kinds of radars. And that pretty much is the order in which you see them. When our aircraft is flying along a border, say, our aircraft, the ones I worked on, tend to stay way back from the action, like 200 miles back, because they are vulnerable to surface-to-air missiles, and they want to keep out of range. So the first thing they tend to encounter is the enemy early warning radars. Those are long-range radars that sweep over a large geographic area, and just they might hit a point every 10 seconds or so and come back and forth. Once the early warning folks have found the target, the height finders come into play. They locate the elevation of the target. Once those two have done their thing, a tracker lights up. And the tracker basically follows the target. He'll go into a spiral pattern until he finds the target and stays with it. So he tracks the target. Fire control, that's when it's getting serious. The surface-to-air missile sites have fire control radars. And when those boys light up, somebody is in trouble. So our goal as on the reconnaissance end is to tell whoever's in the neighborhood, either take action, take out that radar, or get the heck out of the way. Active and passive. Okay. The reconnaissance business that I was in is passive. We are not transmitting any signals. We are sitting in the background, vacuum cleaning up anything that's out there. Our aircraft typically have about a dozen workstations. The aircraft I'll show you a picture of is an RC-135. That's a military version of the Boeing 707, which has been around since the late 50s. And we have still got those things flying. And we keep them up to date, keep them going. The active folks, AWACS, for example, is an airborne warning and control system. It's the big Boeing aircraft with the big dome on top. They are air traffic controllers. They're sending out radar signals, locating everybody around, identifying them, doing what they can with them. We were strictly passive, intercepting and identifying everything we could find. Okay, here's some pretty airplanes coming. Isn't that a beauty? That is an RC-135. Its name is rivet joint. That's what the Air Force names things, rivet joint. If you look at it carefully, you will, is there a laser on this thing? See the big nose? That's an all-weather radar nose. Big, heavy-duty radar looking out far into the future. See the big engines? These engines are from the Boeing 747. These got upgraded from the little engines that it used to have. See the multiple antennas across the top? These are communications antennas. This guy's got to communicate with folks. Cleverly, I can show you this. These cheeks, side cheeks, these are the E-link cheeks. These are the radar receivers behind those cheeks. That's where the E-link stuff is. Cleverly, this is my model. It's got the little engines. Now, the fun thing about this is, these antenna arrays, see that little array sitting there? The little bigger one back here? See these bigger ones, these toadstools sitting here? You can't see this one back here. But it's got about 4 different sets of antennas that are built for direction finding in different frequency ranges. Rule of thumb says that the length, the spacings between the antennas is a few multiples of the wavelength of your signal. Wavelength of signal. The only one I can remember is 10 gigahertz is 3 centimeters. Got that? 10 meters. 10 gigahertz, 3 centimeters. Take it down. 1 gigahertz, 30 centimeters. Order of magnitude. 100 megahertz, lost it. 300 centimeters. 3 meters, 10 feet. So by the time you get down to 300, you want multiples of 10 feet on your airplane? We don't have that much real estate. So when you get down in the hundreds, the antenna arrays have to get too big to do much good. Anyway, I'll show you one more thing about that airplane. See that thing back there? Back when this airplane was born, it was a tanker at an airborne refueling station. Its tanker boom was in that pod. Nowadays, it carries a 6,000-foot, very low frequency radio antenna. It just belays it out behind it. It's hanging there in the air. They get lost, they get tangled, they get cut off, they flop on the ground. Don't see them with those airplanes. Here's a whole bunch of them. These are called Cobra balls. They are S&T aircraft, scientific and technology. S&T. They got the big nose. One thing that's subtle that I bet you don't notice. Oh no, I lost it. Still lost it. What color is that wing? What color is that wing? What color is the next one? Can you tell? It's black. Why is it black? Why do football players put black under their eyeballs? Cut down reflections. This old boy does infrared detecting. Who out there uses infrared? Why would you use infrared? He's looking at missile launches. When the North Koreans launch a missile, this old boy is up there flying around with his infrared windows sitting up there, looking out to the left, and the signal is not bouncing off that black wing. He uses spectral analysis to determine the fuel mixture of the North Korean missiles. That's one of his jobs. These pods down the side, these are event antennas behind there. He's got the big nose. A lot of these fly out of the Aleutian Islands off of Alaska. So they tend to have very heavy-duty landing gears. They're landing on rough, sometimes icy runways. That's a fleet of Cobra balls. Moving right along. This is an AWACS. AWACS is Airborne Warning and Control. Oh, I meant to tell you. The two we just looked at were built and maintained by the company that I worked for, which was E-Systems when it started. It was bought by Raytheon, later bought by L3 Communications. This aircraft here is maintained by Boeing. It's Airborne Warning and Control. Basically, it's a flight coordinator. He keeps track of every airplane in the area of interest. He has identified all of the friendlies. He tries to identify all the hostiles. And he indicates the ones he does know as unknowns. He's a flight controller. This, see the JS on the tail? That's Joint Stars. Joint Stars is a joint program between the Air Force and the Army. The radar is on the bottom. In that canoe there, it is a ground-looking radar. His goal is to find things on the ground, moving around. Particularly of interest in military convoys. Now, military convoys typically have a Jeep or something leading it, something got a tail of it, lots of airplanes, lots of trucks in between. The guy at the front and the guy in the back talk to each other. Guess who's listening to that conversation? Rivet joint. We identify the convoy, we tell who they are, where they're going, and tell this guy. He's got the map of the convoy on his display, so he knows it. We've identified it. So that's some cooperative kind of effort going on there. Moving right along. This is a Navy, I think it's called a Hercules. It's a carrier-borne airborne traffic controller. So he's working out over the oceans. This is a Navy P3. See the boom on the tail? That's called a MAD, magnetic anomaly detector. He's a submarine hunter, marine patrol, looking for submarines. He also carries depth charges. So if he finds a submarine that looks unfriendly, he can drop depth charges. For those of you old enough, my age, the Navy P3 is the militarized Lockheed Electra. Anybody remember the Lockheed Electra? It was a turboprop aircraft built in the 50s to compete with the oncoming jet aircraft, like the de Havilland Comet, those kind of things. It fell apart in the air. Why? They could not analyze the nonlinear couplings between the engines and the wings and the fuselage. At certain speeds, up in the 400 to 450 knot range, they would set up oscillations, break the wings off. We had several of them crash until they decided not to let it fly above 200 knots, maybe 250 knots. But it's built for 450. But they thought it was built for 450. Anyway, they're still flying. There are literally hundreds of these on maritime patrol around the world. They're out there looking around. This is a German aircraft. That's the only airplane I have ever seen back into a parking place. They can feather those props and vacuum into a parking place just like you'd back a truck. The German aircraft, recognize the stinger on the tail? He's another maritime patrol airplane, Germany. This, it's a Hawker, I believe. It's a British airplane. This came to life as the de Havilland Comet. Does anybody remember the de Havilland Comet? Sure, there's somebody old enough. It was a British passenger aircraft, again in the mid to late 50s. See the little windows on the top? See the cute little windows? When the aircraft was originally built, they were square. What happens to stress distributions in the area of corners? Anybody know about stresses on corners and how they tend to split? The blooming windows blew out of the airplane. They changed them to round ones, but we lost several de Havilland Comets because the compression and decompression cycles fatigued the metal around those windows. And when they cracked, the window blew out. And sometimes took the whole side airplane with it. So it's now a military aircraft flown by the Brits, routine patrol, moving right along. U-2, Lockheed aircraft. You know, one thing I'm supposed to be saying is the companies that build these aircraft have jobs for mathematicians, computer scientists, and engineers. The Joint Stars was the AWACS is a Boeing aircraft. Applied to Boeing for jobs. The Joint Stars is a Northrop Grumman aircraft. Applied to Northrop Grumman for jobs. They got jobs in Florida, jobs on the West Coast. This is a U-2 built by Lockheed. Lockheed Skunk Works in California. It's a high flyer. I think they're still flying. It's been flying for probably 40 years or more. But anybody remember Gary Powers? There's bound to be one or two. The Russians shot down one of these. These old boys fly in excess of 50,000 feet. Very few airplanes at the time could get that high to shoot it down. But a Russian MiG shot one down over Russia, unfortunately. We got to get the guy back. How about this one? Oh, Blackbird, SR-71 Blackbird. This is another Lockheed Skunk Works project. This one is a trainer version. See the two cockpits, one here, one here. Most of them have a single cockpit, or a single pilot. So this is the trainer. This old boy holds the speed record across the U.S., crossing from the West Coast to the East Coast in excess of Mach 3. This old boy can move. It's built heavily out of titanium. When it's sitting, there's one in the Smithsonian Museum here in space. When it's sitting on the ground, it leaks. When it gets at altitude, it tightens up and everything's fine. The future. This is a drone. It's called, I can't call it, Global Hawk. It's a Global Hawk. I believe it's built from Northrop Grumman. It's a drone. I think it has about a 90-foot wingspan. We use it for intelligence gathering of all kinds. It can do photo recon, it can do direction finding, it can do all sorts of stuff. But this is going to take my old job away. Okay. Some sample targets. What are we looking for? We look for SAM sites, surface-to-air missiles. We look for command and control communication stuff. We looked at radars. Yes, that is a Russian SA-8. It's a surface-to-air missile. You can see the missile tubes back here. See the radar antenna. I think there are two antennas on there. There's a big one here, small one here. But those are the fire control antennas. So we look for those. We want to know where they are. Back when I started this business, back in the early 80s, we looked for them, and we take our tapes back to the people who were going to analyze them, and they looked for them, found them. Next day they went to look for them. They weren't there. They were mobile. So, you know, they hide them under trees. They hide them under tarpaulins. They hide them. So our goal was to find them fast and act on them fast. This is an SA-10. This is a big one. That's probably a Scud-sized missile that's in those tubes right there. Not real sure what he carries. This is an SA-13. You see the ones on top. Okay, enough of that. The target process. Signal arrives at the antenna array. Carefully designed antenna array. Cleverly designed for direction finding purposes. Electrical engineers are hung up putting antennas in a row. Equally spaced line of antennas. That's not optimal for direction finding purposes. So we designed our own layouts, optimized for direction finding purposes. What we do is measure the phase difference as the signal hits pairs of antennas. Typically, we'll dwell on a pair of antennas for like 30 milliseconds. Another pair, 30 milliseconds. Another pair, 30 milliseconds. Another pair, 30. Typically 4 to 5 pairs of antennas. And pick up about 5 phase difference measurements. Then we convert those phase difference measurements to direction of arrival. We have an equation that relates phase to direction. I'll show you that in a minute. I'll see. Once we have gotten the direction of arrival, we establish a locus of position. Most of the time we call those LOBs, lines of bearing. But depending on your geometry, that locus of position might be a great circle on a sphere, or it might be a geodesic on an ellipsoid. Let's try saying that fast. Try processing a geodesic on an ellipsoid. Do you know that requires an elliptic integral to evaluate? You don't want to do that. Okay. Moving right along, we roll together many lines of position with LOBs, target location. This is basically fly, line of bearing. A little bit later, line of bearing. A little bit later, line of bearing. Intersect a bunch of lines of bearing, put an air ellipse around it, call that the solution. So we will talk about some of that. Hey, that's it. The next one. What's the next one? How do I get to the next one? How about you find it? Yeah. This one is called Airborne Reconnaissance. Hot diggity dog. Triangulation. Specially prepared for this audience. I tried to give it to the College for Seniors at Appalachian State University. Lost it in about 5 minutes. Huh? UNC, I'm sorry. UNC, I should get the universities confused in that. As my senility advances. Prerequisites, analytic geometry. You know, experts in plane geometry, spherical geometry, and ellipsoidal geometry, right? You can do geodesics on an ellipsoid. Linear algebra, y'all can multiply matrices, no big deal. Calculus, minimize a function, that's what we do. Statistics, relate noisy measurements to noisy results. It is automated vector direction. I just said all this. Okay. In the spherical Earth world, a line of bearing becomes a great circle on a sphere. You know about great circles on a sphere. Suppose we choose a tangent plane on our sphere in our area of interest. A great circle defines a plane through the center of the sphere. The intersection of that great circle plane with our tangent plane is a straight line. So all of a sudden our problem becomes, a line of bearing that's a straight line. So our great circles, the logs on an ellipsoid, they're basically impossible. You can generate them, but you can't solve them. You can't work that kind of stuff. So we're going to proceed with the spherical. I'm going to show you a flat earth solution because it's so easy and so nice and so fun. This is kind of how it looks if we have multiple observers. We have one observer sitting up here at X1, Y1. He measures a line of bearing. Now, the angle is measured from north. So all of our trig works from north, clockwise, and counterclockwise. Observer number 2, we have his position and a bearing. Observer 3, position and bearing. Skip something? Yeah. Probability question. Given 3 lines of bearing and the triangle that they form, what is the probability that the target is in that triangle? Give you some hints. Each guy who's taking a line of bearing is dealing with a random process. So his line of bearing measurement ought to center where the target is with a normal density function around that point. So he's on the right side half the time, on the left side half the time. That's true for each of our observers. So there are 8 cases. Everybody, well, each guy's either right or left. 3 of them, 2 to the third, 8. 8 cases. Of those 8 cases, 3 of them form a triangle that contains the target. So only 3/8 of the time is our target in that triangle. So you better expand your search. Get out of that triangle. We take lots of lines of bearing. But I'm using this because the miss distance is what we're going to look at. I want to find a point that minimizes sum of squares of miss distances. So I've got to find those miss distances. We're going to choose the test point, calculate the miss distance, form sum of squares. Anybody can do that. We got to have the equation that the point is on the line, the miss distance for the point off the line. Here's the equation determined by our line of bearing. The direction vector, sine, cosine. You probably thought it was going to be cosine. Because if we were measuring off the x-axis stuff, it would be. We're measuring from north down. So we're interchanging the sine, roles of the sine and the cosine. So our unit vector is sine beta, sine b, cos b. We have target location. That equation at the bottom of the page is the equation of that line. X is our unknown traveling along the line. T is our parameter. X1, Y1 are the positions of the platform. 2 equations, eliminate T to come up with our pretty standard straight line equation. Right there. Moving right along. Off the line. This is where it gets to be fun. We have our target, which is not on our line of bearing, and we want to estimate the, where'd it go? We want to estimate that miss distance. How do we do that? We create the normal to that position vector. See the normal? How do you create a normal in 2 dimensions? You swap the coordinates and change the sign of one of them. Got that? Swap the coordinates, make it cos and sine. Cosine's acting like an x coordinate. It's the negative one. So you can observe that those 2, the n and the original, are orthogonal. Take the dot product. You get minus cosine plus cosine. Orthogonal. Wonderful. Now, form the dot product of that distance with that vector. What do you get when you dot it? You get that projection, that distance. That distance is the same as that distance. So we can estimate the distance in terms of our unknown location xy. What we're going to do, there it is written out in dot product notation. Capital X is the unknown vector, x1 is the position. Dot product. So here are 2 equations, point on the line, point on. See, if we'd been smart, we'd have done this one first, And the point on the alignment had d equals 0. But we weren't that swift. Alrighty. So each line of bearing is characterized by an observer position, x, k, y, k, and the normal vector that contains the bearing angle information. So here, here is our normal vector. It's a row vector. One this distance equation looks like that. It's just a dot product. A whole bunch of them looks like that. We typically work with dozens, 25, 30, 40 if we need to. In matrix form, the in matrix is that these are our normal numbers, normal places. X, Y is our unknown, B is our, it contains the normal data along with the platform position data. And the distance is the distance. So in matrix language, our sum of squares of error is D transpose D. There's D transpose. We located our distances down a row, distances down a column. Column times the row gives you sum of squares of distances. The nx minus b transpose nx minus b is the right-hand side. Not all I'm going to say about that is it's a quadratic form. The unknowns are buried inside the x's. Quadratic form. That's the sum of squares of error. How do you minimize the sum of squares of error? You take the first derivative and you say it equals 0. All righty, sports fans. There is the first derivative. N transpose nx minus n transpose d equals 0. Or solving for x, x equals, right there it is, n transpose n inverse, n transpose d. Now, that probably looks a lot worse than it is. How big is n? It's n rows, 2 columns. N transpose, 2 rows, n columns. What do you get when you multiply? A 2 by 2 matrix. Can anybody in the house invert a 2 by 2 matrix that is symmetric and positive definite? A, B, B, C. To invert it, you interchange the A and the C, put minus signs on the B's. C, B, minus B, A. And trivial. Even freshmen can do that sometimes. Okay. So we have the solution. N transpose N transpose. That's a 2 by 2 matrix. How big is N transpose B? See, N transpose N is 2 by N, and B, how big B was? Is it N by 1? I think it's N by 1. Anyway, I'll say it jumps out and move on. What have we done? Okay, that's the easy stuff. All right. Now we want to get the noise into the problem. Nobody has said how noisy these measurements are, so we're going to do some noise. That's what we started with our varying angle error. See our varying angle error there? Is basically that distance divided by that range. Now that's actually the sine of the angle. But everybody knows that for small angles, the sine of the angle, the angle in radians, and the tangent of the angle are all about the same thing. Good enough for government work. That's what we do. So our angle error is that misdistance divided by the range. Many sources of angle error. Instrumentation error. That is our phase, our array that's measuring the phases might not be all that great. We don't know where the target is. I'm sorry, we don't know where the observer is. When we started this business, we didn't have GPS navigation. We just had dead reckoning navigation. So we might have been miles off of where our platform was sitting. Atmospheric perturbation. RF waves kind of wiggle through the atmosphere, where it's denser and less dense. Stars twinkle because of atmospheric perturbation. Many more. So we got a whole bunch of them. And Chebyshev used to say, you put enough crap together, it comes out normal. But basically, the errors that we end up with are Gaussian. Of course, they mean zero because we're good, unbiased, and we have a known standard deviation. We know that because we fly these systems against known test targets all the time. We calibrate them. We analyze the noise. If you give us the signal-to-noise ratio of the incoming signal, we will tell you the sigma of the measurement error. You know, we're that good. So that's what we did. Now it gets good. We take our measurement errors and take our delta bearing, our bearing angle measurement, and divide it by its sigma. What does that do? What? I can't turn it off. Okay. It standardizes our error to a unit normal. It's a normal 0, 1. Mean 0, 1 sigma. Isn't that clever? Clever. So now we have a new system of equations. Well, where did that R come from? Now, what is it? Remember that we've already solved the problem once. It might not be the ideal solution, but it's better than no solution. So we use the X estimate that we got and calculate the range from each of our platform positions. And we associate the appropriate sigma with that measurement. Moving right along. The old misdistance equation and the new improved one. All we did is divide our distance thing by the range and the sigma. Same thing over here. This is our normal equation stuff, divided by the range and the sigma. Come on. Hung up. I'm stuck forever. Try again. Okay, new improved problem. We want to minimize the sum of the squares of the modified errors. New improved errors. And all we have to do is modify the normal and modify the lee side. Okay. This is what our new individual equations look like. We've got that R sigma on the bottom of all of them. Oh, no. Going too fast. So our normal vector is modified by dividing each component by the R's and the sigmas. I put a star on it to indicate it's something new and different. We knew how to solve the original system, this nx minus b. Now we have e equals n star x minus b star. We've upgraded our n's and our b's to use our information. Original solution, n transpose n inverse, n transpose b. All we have to do is same song, second verse. It's our new and improved normals, our new and improved b. Do it again. Pop it out. And it's fast. Now let's see what happens next. What did we just do? We solved the distance problem. We used the solution to calculate the ranges. We incorporate the ranges and angle standard deviations into equations. We solve the sum of squares and angle error problem. And we have a solution. Another solution. Now, we provide the estimate of the target position, x star, y star. Or we provide longitude, latitude coordinates. Everybody in the world says latitude and longitude. I worked in the world of longitude, latitude, altitude. Why would I put them in that order? Longitude, latitude, altitude. Instead of latitude, longitude, altitude. It's the difference between a right-handed and a left-handed coordinate system. In the world I work in, coordinate systems are right-handed. Here there's X, Y, Z. You rotate X toward Y and you get Z. Right-handed system. If you say lat long, people will put the data in as lat long altitude. And you can't do it. You can't do matrix arithmetic on a left-handed system. I guess you could, but the world's used to right-handed systems. Work in a right-handed system. Okay. The grand finale is to deliver the location with a 95% confidence ellipse. The center of the ellipse is the estimate of the target. The ellipse's semi-major and semi-minor axes provide the size of the ellipse, and the orientation angle of the major axis shows the orientation of the ellipse. Now, okay, we're doing random processes. Best we can do is a probability density function. So what we deliver to our customer is a probability density function, which is two-dimensional Gaussian. Well, don't say Gaussian. Engineers always say Gaussian. It's a normal density function, 2 dimensions, characterized by its mean and covariance matrix. If I had time, I would tell you what the covariance matrix is. The covariance matrix actually is N star transpose N star inverse. Well, how does that come about? The next lecture of 25 slides will show you how that's done. I think I'm not going to do it today. Anyway, once we have that covariance matrix, it's 2 by 2, symmetric, positive definite. Therefore, it has real eigenvalues and orthogonal eigenvectors. The 2 eigenvalues give you the size of the 1 sigma semi-axes, and the eigenvectors provide the directions of the Eargle ellipse. I could spend another half hour and show you how that's done, but I think that's not going to happen today. Come on, come on, come on. Man, this thing loves to stay on. Normal density function, 2-dimensional density function. Bell shaped in both directions. That's it. These are some typical contours of that normal density function. Now, the little blue one is the 1 sigma Eargle ellipse. The next blue one is the 2 sigma Eargle ellipse. The big blue one is the 3 sigma Eargle ellipse. The big green one is the 95% confidence Eargle ellipse. That's the one the customer loves. Got to have a 95% confidence. The red one, oh my goodness. The red one that's horizontally oriented is the 50% Eargle ellipse. The vertical one is supposed to be a circle. It's plotted as a circle. The graph is a circle. That's the CEP. The CEP is the circular error problem. And normally, for the artillery folk, that's the contour that contains half of your hits, and the exterior is the other half. Not through yet? Okay. We started this business, the Eargle ellipses were tens of kilometers. By the end, they were down around 80 by 50 meters. It's football size things. Okay. TDOA and the radar are much more accurate. Okay. The way we solve these problems, in 1 minute or less, the Earth is modeled as an ellipsoid. At the time I was working, it was the WGS-84 ellipsoid. In the neighborhood of interest, we find the osculating sphere. You remember from early calculus what an osculating circle was? Now the curve, you find the circle that fits that curvature best. The osculating circle. The osculating sphere is the sphere that fits the ellipsoid best. The ellipsoid has a north-south radius of curvature and an east-west radius of curvature. The geometric mean of those 2 radii of curvature is the radius of curvature of the osculating sphere. Now we've got a spherical problem. With our spherical problem, we can lay down a tangent plane. Tangent plane on a sphere, our lines of bearing become straight lines. So the way you solve the problem is to solve the spherical problem and to solve the tangent plane problem. So that's how it's done. And we do it multiple times. As your estimate of the problem location, target location gets better, you put your tangent plane there. So it's perfect as you're going to get. Surely I'm through. Yes, through.
Any questions?
Yeah, I have one. So when I'm sensing from the plane, there is this third dimension. I'm really I'm in a three-dimensional world.
Yeah.
But is the fact that you're looking at something 100 miles away and you're not 100 miles up, do you ignore that or do you filter out that height? Or because the observer has height in addition to the...
The airplane in the comment world is calibrated at -5 degrees. And we declare that the angle we measure at -5 degrees is the angle in the horizontal plane.
Okay.
This is what we do. And that -5 is set so that, I think, from the altitude these aircraft fly, the horizon is at -3 degrees. So we want to be able to catch things on the surface from -3 into about -8 or so. So -5 is about the same. So we calibrate it, and our calibration table contains phases and the angle of arrival at the aircraft when we flew it against the test target. ELINT's different. In the ELINT world, they sometimes have a two-dimensional antenna array. So they can detect both the azimuth and the elevation and the azimuth. So, I mentioned wavelengths. In the comment world, they're big. In the ELINT world, they are tiny. So you can get along with little bitty antenna arrays. Another problem in the comment world is that pieces of the airplane are comparable in size to the wavelengths. That distorts your wave field. So we have to deal with that. I quit.
Any other questions?
Yeah.
I wonder if you have any career advice for our grad students who may be embarking on an industrial career
Well,
soon.
I named half a dozen companies. They actually have analytical groups that hire mathematicians. They have big software groups. All of this stuff is software driven. It's automated processing on the aircraft. Our operators have big workstations. And basically everything they do is push buttons and automated things happen. And those automated things are done by software engineers like my beloved wife, who did that for many years. So yes, the defense industries and the big ones, L3 Communications, Northrop Grumman, Lockheed Martin, Boeing, that's a pretty good start. And they have jobs. And they're also notorious for hiring for a contract and then laying off. The contracts last a long time.
So, Patricia, may I ask you to come here? We, as a department, would like to thank you both for the small gift as a token of our appreciation. One of our students, greatest students, we have gifts for you. And here, by the way, you have T-shirts created by our graded students.
Okay.
One for you and one for you.
Very good.
So thank you very much again for your gift. And we
Okay.
will continue with the reception in the lounge right now. And if anybody wants to join the undergraduate talk, the talk for undergraduate students, and listen to even more interesting stuff,
Different stuff.
different stuff.